OK，会不会有一大声的感觉？等一下，喂，OK。All right, we're gonna start with the last class today, and yeah, I had some errands to do this morning, so thanks for understanding. We're starting a bit late today, but then I mean it's gonna be a light lesson. It's the last one. Before you launch into this, as usual, just to make sure, I saw that everyone has handed up the backprop assignment 2, and that you should be busy finishing up assignment 3, the last one, which is going to be due in, I think next Friday, yeah, June 19th or something, okay? I have to submit the grades by June 22nd. So if you need, an extra day or 2, that's fine, let me know, but I think you should be able to do it by 19th. But there's not much more room I can do for that because 19th and then I still need time, and then like 22nd I have to submit the grades, okay? So I believe you should be okay, work hard towards getting it. If you encounter problems, let me know earlier rather than later if you need help in between. I mean, obviously I'll still be available on email and all that kind of stuff, okay? All right. So any questions about all of the class things that are required? Everything that we talk about today will not so critical for your assignments, all right? So anything regarding the previous course, things that would be important for you in terms of the hot view, the backprop, and the von Malsberg. Okay. I've seen some of the solutions that you guys have been using in at least the hot field network. I've given you some comments, and I think everyone does great, and it's nice because I see that you guys also are trying your own ways and then expanding on things, and that's the way it should be. Okay. So and I hope I haven't looked at the backprop yet, but I think I've taken a quick look, and it more or less you guys are at the right tone. And so I hope that for the VDM, the von Malsberg, you guys can have a bit more freedom to explore, because since the assignment doesn't, it's not as structured, then you can have more room to explore. Okay? So I'm very excited and interested to look at all your data and all your submissions. Okay, so then in that case, we're going to quickly launch and finish up. These are just some other issues that we will talk about to kind of bridge the gap between what we do in this class, which is very so-called fundamental and basic, and from a more psychological and biological point of view, and sort of to try to bridge it with, obviously, we live in a world where the large language models and the other AI applications are the so-called norm or bulk of our exposure or understanding of AI, okay? And so where does what we do kind of fit, or what are some issues that, how did we move from all these basic level stuff to what we see in the large language models these few days, right? Are they very different? Are they kind of like completely not relevant? How are we relevant to them, or how are they not relevant to this problem? There's no we or they, sort of. Everyone is doing the same thing, but are the problems being addressed or examined really all that different? And is there no crosstalk or no relevance? And I think the conclusion is that there is relevance, right? And I think it is important to appreciate first, for historical reasons, this is very important. For historical reasons, all the large language models, as long as they are neural networks, which they are, were started because of biological discovery, right? Somebody somewhere, long time ago, cut open the brains and then saw that, hey, our brains are made up of neurons, and how neurons work, how the brains work, essentially comes from how these neurons connect to each other. That very, very simple, basic discovery was what inspired that. Now that when we have computers and computation, that if we try to model or use this phenomena that we observe, this idea that we observe, how living systems process information, that we can then translate that to a electronic digital media and then have that process information in the biological way. Because remember, we already have calculators and logic gates and transistors. We can process information that way. But the idea of shaping it, at least software-wise for now, to mimic how a biological system processes information, right? That kind of an approach was inspired from biological discovery, okay? So the linkage is there. And then also, like, in terms of validating it, validating the language models, validating the AI nowadays, is really also benchmarked on how living systems perform, right? We train our language models because we use language in a particular way, right? So it's very intricate, and I think it's always very important to not forget this fact, because sometimes if we focus too much only on the biological part, and then we forget that, hey, if we scale it to a kind of an engineering solution we see nowadays, we forget that things might be different, you know, when we talk about scale. And alternatively, when we're talking about scale, we might forget that, hey, actually this comes from some fundamental things, and so if we deviate too much and our goals kind of lose track too much, there might be something that would be overlooked or lost. So it's very important, I think, that people always try to have cross-talk, interdisciplinary talk, and to try to be able to communicate and understand what different people from different fields, because this AI field and neural networks field is a multidisciplinary field. And so it's very important for people, for you guys in the future, to be able to talk to each other in different fields and not to kind of forget that, because it's very easy to lose it. It's very easy to just talk about your own thing and then you don't care about what other people are doing. That's easy and very comfortable. And you will get the rewards from that. You will be able to dig deep into your field, but you might lose out like what happens when you have crosstalk, okay? Which is actually what neural networks come out. It was crosstalk from biologists to computer scientists, right? And mathematicians and physicists and all that. So I hope that by having this course as your kind of one of your fundamentals, that in the future, if you do deal with this kind of thing, you will remember that, you know, there's always an important aspect of being able to translate between disciplines. With regards to neural networks, it is this discipline from a biological, psychological point of view, with the more technical and computer science and engineering point of view, that these two really need to have a deeper crosstalk, okay? So that's the linkage that we're trying to bring out at the end of this class, at the end of this course, to remind you sort of that where you are at. To make it a little bit more concrete, you might be thinking about, you might have heard of some of these architectures: recurrent neural networks, convolutional neural networks, and then you will hear deep neural networks and other sort of neural networks. But essentially, there's these two parts. You might heard of transformers. You might heard of LSTM, long-term, short-term memory, which was prior to transformers. And then, you know, there's always new kind of sub-architectures. These are all labels and terms for specific, architectures of neural networks, each having their own property. But if you read Agarwal, they will cover that. There's also radial neural networks, blah, 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 right? But essentially, you can sort of safely think of these neural networks, whatever architecture they have, they can be sort of, I wouldn't say categorized, but at least related to these two classes, at least of different types of neural networks dealing with different modes of information, specifically time for recurrent neural networks, things that are happening in time, or modeling how information transitions over time, okay? And obviously space, how information has spatial associations, right? All the other neural networks, transformers, LSTM, all these others are either dealing with time or space or some combination of both. Okay, so I highlight these two because they bring this out, this dichotomy of information transitions most easily. Yeah, the transformers and all that becomes a little bit more complex because they have some specific parameters that are very, very, very specific. Okay, so for example, transformers is about attention span, sort of, right? Which is attention span is about time and space. Okay, so but I don't want to use that as an example because it's like too specific. Something more general and more fundamental is probably better for understanding. So let's talk about RNNs, then CNNs, and then we'll talk about overfitting, which is also not a specific problem just to neural networks, but it is a problem in all modeling, okay? Machine learning statistics itself. But we'll highlight about how overfitting applies in a neural network case. Okay, so let's talk about RNNs first. And okay, and the best way to talk about RNNs, which is recurrent neural network, is to draw an RNN, and I'll show you amazing thing, and you find that it's at core how LLMs kind of got inspired and started. Okay, a typical RNN would look something like that. So I have, Agarwal has that. This is the input, okay? And it has some weights to some core hidden layer, okay? And this is weights, okay? If I draw it like this is a multi-layer perceptron, right? We can say this is weight 1 and weight 2, okay? When I say W1, I don't mean just one number. I mean like a whole array of weights, okay? And each of this input and hidden layer, you can imagine, you've done that in your multi-layer perceptron. It can be 8, 4, 8, 5, 5, 5, 5, 2, you know what I mean, right? You have these different layers and depths of architecture. It doesn't matter, it's as long as one is upstream, AI, and then you have a hidden AHs, and then you have the downstream AJs, and in between the AH can be wider, smaller, whatever, and correspondingly you have the weights, right? Each of these can have backprop, right? So you can have delta here, correct? And then you can backprop the delta. You can forward propagate the activity based on the input. So let's say this is the stimuli, okay? Okay, and then this goes all the way up, gives you an output AJ, you compare it, you get a delta, come back, and then you adjust the weights accordingly. This is an MLP. Where is the recurrent neural network is if you do it this way. Okay? Let me okay, let's not have the S. Let's not have the in at all. Let's just say that this is stimuli 1, stimulus 2, delta 1, delta 2, so to speak. And again, these are that you have the corresponding. It's the same network. So the recurrence is that you have a same network, but then you carry over the weights from the previous instance, and it affects those weights at for the next instance. So there's recurrence in that the previous states can also recurrently affect my current learning state, right? Because if you take out this part, this is itself also the MLP, right? But this MLP is influenced by its previous state, correct? So there is a recurrence there. Okay? And I can do this ad infinitum, keep going on and on. I have input, I have output, so on and so forth. I can keep doing this. If I do it this way, this is very interesting. If you read Agarwal, you can essentially encode a human language sentence. Okay? For example, I can do this. A sentence called, "The cat chases the mouse." I can frame my modeling goal as I want to be able to predict what's the next word based on the current word. Okay? So if I give you the word "the," your model should, as the input, the model should give you the word "cat." And if I give the model the word "cat," then it should give me the word "chases." And if I give it the word "chases," "the" again, then "the" again, then "mouse" again. There's a problem. There's two "the's." How do I know, is this the first one, which would give me "cat," or the second one, which would give me "mouse," right? Okay, so there is a little bit of an issue there, but we'll get to you'll see how it works. So for example, the idea is, if I have an input "the," I want it to output "cat." After I trained it. Let's say I have a whole database and I keep training it, okay? You can imagine something like that. Then if I give you "cat," then I should give "chases." And then if I give "chases," it should give me "the." And then if I give it "the," mouse. And that would be how you can generate a sentence based on cues, right? I can take the first cue I have to generate, I say "the." But after it generates "cat," I use its own output as its own next input. And then eventually you get a whole sentence. Okay? This, I'm talking about it as a descriptive, right? We don't have the exercise for you to go and try it yourself. But in theory, I can make this as assignment 4, right? And then you guys should be able to, you now understand how to work this, right? You have the data table. You create the architecture like this. And then you think of how to frame it. You don't have to just use this example. You can use all other type of set of stimuli, other sentences. The dog ran after the cow or whatever. You have all those data tables. You can make it, you can train it. You can totally do it, okay? It's just whether you want to spend the time to do it. But you can imagine how, if you set it up and you think of things this way, that you can totally make your own sort of RNN like this. So how does this work? Well, because essentially what these weights are going to do after you've trained it, right? You give it this sentence. This is the data table, right? Humans do this. This is the stimuli, the data table that I want the model to learn, so that if I test the model, it would give me this answer if I give it accordingly the stimuli. And what actually does the model learn? What does this RNN model learn? It learns the state-to-state transition matrix. So for every token, okay? And tokens must be unique. So we only have 4 tokens in this sentence, right? And essentially, you have the cat chases mouse. Okay? The cat, and you can make a token-to-token transition matrix. okay? Itself to itself, the probability or the transition weight is always 0. It doesn't in general, right? I mean, you could, but then in general, this does not happen. But from the to cat, the probability is 1/4, right? 1 out of 4 times the is followed by cat. The is followed by chases, 0. And then the is followed by mouse, 25% of the time. It may not be adding up to 1. You can make the weights. You can play it so that your transition matrix always add up to 1 and all that. But you can play a simple game first, just to make it understand, is that I have 4 tokens, mapping to 4 tokens. The probability with which this token leads to the next one is 1 out of all the 4 possible tokens. And they don't add up to 1, but that also captures the fact that, right, not every word will always have some result. Similarly, cat is never followed by the, so this is asymmetric. Well, why it always has this weird color? You want to make things confusing for people, so keep the same color. Yep, it's not symmetric. So the cat is not the same as cat the. Okay? Cat chases. 1 out of 4. Cat mouse, 0. Chases the, 0. Chases cat. Chases, chases the has. So, and the mouse, 0.25. And then cat mouse, 0. Mouse chases, 0. This asymmetric matrix sort of represents this sentence. If you understand what the matrix means, if you plug it in correctly, you can sort of regenerate. Because it's asymmetric, this is always this followed by this. So this is always 1 to 2, right? A 1 to 2 direction. So there's no 2 to 1 direction, okay? So if you read it like that, technically speaking, this matrix is exactly that sentence, mathematically. It is the graph of that sentence, okay? The only way, or you find a transition matrix where the only way that you can have these numbers is, this set of numbers will, and so that if you implement and drive this through, you will retrieve the sentence. In fact, this is what we call an embedding. Okay, so there's a lot of implications here in matrix theory, in graph theory, in mathematics, where actually this is the computational graph instantiation of the matrix. We have found a solution, right, in this form to embed that information. And equivalently, that information is equals to this graph. So that's what we mean by everything can be construed or constructed as a computational graph. Is if you have nodes and tokens and the weights connecting between these nodes and tokens. If you find the right structure, this is equivalent. These two are topologically equivalent. Okay? Moving in this space is equivalent to moving in this space. Okay, that's a lot of abstract mathematics here, but that's how you see if you have an RNN and you train it like this, okay, it is essentially embedding and encoding this information, and that's how it encodes. It can encode a sentence. Okay? Now, this is, I'm oversimplifying it, because what actually the RNN encodes is not just one word and then its very next word. You note that it is carrying over this and this, which means that AH3 has the benefit of this one, and this one, sort of, right? It's not just 1 to 2 and 2 to 3. 3 actually also has 1 to 2, 2 to 3, and 1 to 3 as well. Okay, what does that mean? It means that when you teach it the first the, and then you say the output must be cat, okay, that's the to cat. But when you teach it chases, it's not just cat chases. It is actually the cat chases, right? And when you give it the next the second the, okay, it will actually be the cat chases the, right? So it incrementally accumulates past historical information. And that is sort of what LSTM, long short-term memory, and also transformers incorporate. The idea of attention from prior instances that are relevant to my current computation as well. So let's say my current one incorporates past weights as well, okay? So it's not, so it's not always just this one to the next one, but also what happened a few instances before. All right, so that's how it knows that even though I'm the, and I occur twice, not every time, I'm not the same kind of the every time. Sometimes I'm the first the, sometimes I'm the second one, and there were other things happening before me. All of this should be sort of encoded in the embedding, the transition matrix. And if you do that successfully, if your neural network computes that successfully, these weights, these are all estimates. If it's weights and estimates are correct, to that extent, it will be encoding exactly that data table. Okay, so that's RNN, recurrent neural network. Okay, any questions about this? So we learned a basic multi-layer perceptron, but we see that if we expand it, we can make it do wonders. Okay, I draw it out like that, but to give you even more fancy way, is actually you don't have to draw it out like that. You just have to draw it out like this. So this is an inset, okay? So this AH, AI, AJ. Okay, this is the basic one, right? And instead of having to draw it out all this time, this is the recurrence part. You have the internal loop. That's all it is. It's just rolling. It's like you have one tape recorder and then you roll it over, right? 就是滚在就粘起来. This whole thing is just that one thing. So in some ways, this is an LLM. It's just that the LLM has been massively complicated and rolled out, that's all. Because what it is doing is it is giving you, and you give it a prompt, and it generates its output, and it has been massively trained with different levels of depth and hyperparameters to generate some string of outputs based on its internal transition embedding its matrix. Okay? There's nothing wrong with that. It's a very, very computationally powerful way of representing all our information in a dynamically generative way, right? The difference would be, it's like a video recording, and we'll talk about that next. It's like a video recording. I can record every second, every bit of information, or I can just encode the core embedding, and then when I need to, I play it out. Which one saves more space? The second one, okay? The other one, I have to encode every bit and gigabytes of information. The second one, I just encode the core, and as long as I have the right replaying program, right, I can play it, or I can regenerate it all back. I just have to store the key. All right, very efficient, actually. Okay, any questions, RNN? Yeah, okay, so, I mean, I don't know, when you hear and you see these things, you should totally think like, oh, I can totally make my own LLM, and it's true. I mean, basic ones, all right? And not where you can consume the entire internet and then have a very intelligent thing, but at least within a reasonable scale, you can sort of do it as a demonstration to yourself of how it works. Okay? You have the tools to do it already, all right? It's just you have to frame it in the right way and expect the right way to evaluate it correctly within limits. You are not going to create a ChatGPT with your local computer, right? That is really scale, an issue of scale. And we'll talk also about that later, but then the principle of it, you would see that you can actually do it. Okay? All right, so RNNs take strings sequences and generates these transition matrices, which are embeddings that encode those string sequences, right, in a kind of a very efficient form. Some of you who understand how these operate would recognize that this is actually like PCA or ICA, where you have an eigenbasis. This is the base dimensionality. You pass it through some eigenvalues, it regenerates the entire data matrix. Okay? So mathematically, that's what's happening. Okay, next is CNNs. And this is convolutional neural networks. Okay? And let's see if I have an example here. Give me a second. Okay, I think, yeah, I'll just show you. Let me pull it up and then I'll flash it on the screen. This is LeNet, one of the earliest CNNs. In fact, probably the best, the earliest, I would say. This is the one that I think Yann LeCun and Fei-Fei Li, or whoever way back, they were developing to solve this problem, which is that I have many, many photos on the internet. You have Google Photos, all your photos are on the internet. And then I think maybe Fei-Fei Li, I'm not sure, but people in psychology were very interested in how the brain, because our brain can recognize that when we see a photo, oh, this is a forest, this is a beach, this is a city scene, right? And in the photos, there's cats and dogs and trees and people and objects and all that, and of different shapes and sizes, but they're all cats. Different shapes and sizes, but all cups. Different kinds of configurations, but all forests, right? We have that experience, and they were very interested in, can we get a machine to tell us that when I give it a photo, it will tell me, I see forests, I see inside there are birds and animals. What kind of bird, what kind of animals? I see faces, this is a happy face, this is a sad face, blah, 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 right? We have that when we see a picture. They were trying to say, oh, can we get a machine to do that? And LeNet was one of the first ones to do that. How does it work? So you will recognize this because you are already doing it. You have a 2D matrix, 32 by 32. Okay? Think to now your VDM, which is a hexagonal one, 19 units, but it is essentially also an array. Okay? And each pixel, which is each unit, is either on or off. 32 by 32, each pixel is one RGB value or a set of RGB vector, right? How much R, G, or B? 0.9, 0, 0.1. Maybe this is kind of like light purple. Okay, right? A lot of red, a little bit of blue, no green. Okay? So each here you can say has 3 channels. Although it's 32 by 32, actually, you will have a R, G, B. You can imagine it's 3 layers. Okay, you can put that as an input. All right. Yours VDM binary is either black or white, which is fine. Okay, so if you don't have RGB, you can make it. Oops. If you don't have RGB, it can be a 2D array only. It doesn't have to have 3. For example, it can be just a grayscale. Right? Every pixel is a value from 0 to 255. And the bigger the number, the more intense, the closer it's to white. And the lower the number, closer to 0 is black. And everything in between is different grayscales, right? And you can use that to encode a photo, a picture, correct? Okay, so you have this 32 by 32 picture, and then can it recognize that in this 32 by 32 array, there is a face there, which is the same as if the face appeared somewhere else. So what we call translational invariance. Meaning that if I see an object or a token, if you want, located here, is the same as if the object is located here. It is also the same as if the object was very small versus that the object is very big. It's the same object. Okay? Translational invariance. The recognition that there is this existence of something in this array, okay, that is constant, regardless of its position, size, and or a translation. So translation invariance. Okay, so could it do it? Obviously, the answer is it could do it, right? Otherwise, we wouldn't have all our amazing tools these days, which is that you can do it by using convolution operations. And you can see what it is. Out of the 32 by 32, what you do is you have a window of 5 by 5. And in this 5 by 5, it affects a deeper layer. And this deeper layer takes the input from the 5 by 5. This is the kernel, convolutional kernel. Okay? And it is like your von der Moosburg network, isn't it? Your von der Moosburg network says, I can influence my neighbor or my neighbor's neighbor, but I don't influence further. Or conversely, I am influenced by my neighbor or my neighbor's neighbor, but not here, right? Okay, so you are already doing some sort of convolution. So this is the idea of convolution. And you see that the convolution can, if you implement it correctly, it can recognize some spatial function, spatial information, correct? Some spatial associations. What it encodes, what is the embedding in all of this subsequent network? So in RNN, the embedding is temporal sequences. In convolutional neural network, the embedding is spatial associations. Okay? So that's why I said one is time, one is space. Okay? So all these complicated things is, as you know, what again, you have the tools to understand this. You can see the architecture is, at first it is equivalently wide. So at 32 by 32 goes down to 28 by 28, goes down to 14 by 14, and then 10 by 16. It's becoming more and more narrow, and it is each time taking receptive fields, right? So the kernel is also a receptive field. So it's taking wider and wider receptive fields, right? At first, it is only 5 by 5 in the C1 layer. But at the S2 layer, okay, it is taking now the 5 by 5 from a 28 by 28, which means that is each pixel here is taking maybe a few 5 by 5s worth of information compressed, okay? And then it compressed some more, it compressed some more, it compressed some more. And so it eventually, the pixels, the units here are essentially seeing the whole picture. whereas each unit in the earlier layers are seeing only portions of the picture. That was one of the exercises that suggested to you, like to extend the von der Waals-Berg is if you can get it to see shapes rather than just line orientations locally. So you are capturing more and more, a bigger and bigger receptive field as you go deeper and deeper in. You might be wondering, okay, what is this? Like, how come it's 6? And like, what is the depth there? It is essentially the channels. So like it's, as I said, it's not just about like you have one layer and then you have an immediate response, but you might be breaking that into different channels of response. That's all. So for example, color, okay? You have the same location, but it may be there is how much red, how much green, how much blue, or how much of some other abstract shape, some higher level. So different channels could mean different color, different subcategories relevant to that layer. Okay, so that's what the thickness goes. So as you get deeper, you see that it's a translation from a flat thing to a deeper thing, but also thicker, because more and more channels, right? Because it's like, let's just put it this way. At first, your retina just responds to blue, yellow, red, green energy. Higher, deeper in, our cortex starts to have more complex channels. It's not just about yellow, blue, red, green. It is like different hues of colors already, and this is a deeper concept. And even higher is not just about those different hues. It is like they may have some emotional meaning or something more abstract. As you go deeper and deeper, you have more and more different kinds of, each of these are different filters or different channels that we encode that take in more and more information from a bigger and bigger receptive field. So that's how the CNN works. Again, you can imagine, because you have the VDM, you sort of have these tools. If you wanted to, you spend enough time, you can make your own LeNet, okay, with hexagon input, okay? Now, and there's an added twist here, because in your VDM network, we only ask you to say, okay, I recognize that I'm only looking at the excitatory layer, the state of it, right? Did it become more and more selective, right? Those evaluation plots that we tried to do, the activity probability. Here you see this portion is a key difference, and this is not hard to implement. Is that, so you can take this as, for example, the S4 is like your excitatory layer, but you can use the S4, let's make this as the input, okay? And, oops, if I draw this out, it might be very salient for you, right? Whatever the state of the excitatory layer, you use that as the input to an MLP, a multi-layer perceptron with hidden units, in which it gives you a vector. This one is an n-bit vector output, which can have a delta, right? Which means you can train backprop, correct? And for example, what could this vector be? Cat. Whoa. Dog. So whatever the excitatory layer is responding, you can feed it into an MLP and train that MLP to say, like, whenever you see this pattern in the excitatory layer, say that you see a cat. Say that you see a dog. Or if he says cat, and then you say, no, that's not a cat, it's a frog. So then you flag that That's cat minus frog, the Hamming distance, right, or whatever, and that becomes your delta. And then you retrain it and say, no, 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 this is not cat, this is frog. And then the next time it says frog. Okay? You get this? How this works? You can also totally do that with your VDM, right? Your VDM, you see it and then you feed it into your MLP that you created in BUT assignment 2. Okay? So, here's the term. This is what we call pooling layers or policy. Okay? My policy is if my people vote this way, I will do this action. If they vote another way, I will pool it and create a policy to do another action. That's what all these are. Okay? And I will introduce another concept here is, so in here, there's the idea that you all know that if you use the MLP, you use the sigmoid function to govern the activation function, right? So just like if you say, I have enough of these activities times the weights across some threshold based on the sigmoid function, my output will be closer and closer to 1 or less than 1. Or you can use a ReLU function, which it'll be 0, and then at some point it's a linear increase. Another function that they use would be the softmax function. So in other words, it doesn't have to be a 1 or 0. It can be a probability. All right? And the softmax is going to be the probability of x of I over the sum of all the xi's. And this will always be 0 to 1, okay? Because the activity of one state is as a ratio of all possible activities of all the other states. So it's always a ratio, less than 1, greater than 0, greater than or equal to 0. And this used as a policy or as a pooling layer because what you do is you choose the maximum, the one with the maximum softmax output, right? So that you weight that, okay, because everyone, if this is a very important state, everyone seems to agree, then this ratio will be closer to 1. If this is not so important, then this will be closer to 0, right? So you choose the one out of the maximum of all possible softmaxes, and that is your population's vote, right? Okay, so that's policy and pooling layer operations. So that's how they implemented CNNs. It is just taking all these different receptive field kernels, and then after more and more filtering and extraction, feed these filtered abstractions to a pooling layer, which is itself an MLP, okay? And training it to then generate some text output, which takes from the RNN again, right? Sort of, right? And then that's how those scientists could say that if I give you a photo, you can tell me forest, you can tell me beach, right? Forest, beach, cat, whatever. Okay, that's how it works. Any questions? All right, so then, so I don't have to draw this because it's already in that textbook. Okay, so that would be RNNs, CNNs, and sort of like how to combine the two together. Let's make this a little bit more interesting. Yeah. So in the previous one, we had the RNN. We started with a CNN. I'm going to do CNN like this. Okay. So this one is the CNN part. And then it feeds into an RNN part. With a recurrence, okay, and an output. And you can have a data table. You want to say like this picture, so this picture, I can draw a cat. Okay, this is the photo, right? And then you have human raters said that you ask them simply, please tell me what you see. Humans, right? You get subjects. Please tell me what you see in this picture. Everyone says cat, or some people say dog, whatever, right? So you get a lot of data. So this is the data table. And they feed this data table into this massive CNN, RNN combination thing, and you get your ChatGPT. Okay? Or let's just say ChatGPT at first it was just reading stories, so no pictures, right? So it could tell you stories back. Then later they got smart and they decided to combine the CNN and the RNN, and now you get your Gemini ChatGPT. It can even then generate videos for you because obviously, though, as we said, it is an embedding, and it is precisely that if you drive it through the right process, it regenerates the results of its embedding. Okay? Nothing surprising about that. Well, I mean, nothing theoretically novel about that. It's really simply a consequence of its operation. Okay, so if that's the case, there is this interesting concept here and a bit of creative kind of thinking in that, well, so if we say that these are picture stimuli, and these are arbitrary sequence mappings. Does it always have to be occurring in this format? Like pictures must be encoded in CNN, and sequences or symbol sequences, let's just say it that way, these different types of token modalities, right? Picture associations or symbol sequences. Pictures goes to CNN, symbol sequences goes to RNN type of things. Must it always be like that? And the answer is no. You can transform, you can convert a symbol sequence into an image. How? Well, let's say the cat chased the mouse. That sentence. Okay? And I have my tokens here. The cat chased, and only 4 tokens, right? I can just simply encode it as this. At first, this is 1, 0, 0, 0. Oh, sorry. Why do I write like that? So weird. At time 1, at time 2, at time 3, at time 4, at time 5. Right? Correct? And what is this? I can, so this sequence of vectors encodes the sentence, right? I can just say that this is a picture, grayscale. Take a snapshot, right? These are white color, and the rest are black. So this becomes a picture. This picture is the sentence, correct? And then I feed it to a CNN. Okay, I mean, you have to, of course, adjust things tremendously, but you can recode, remap, or reformat symbol sequences into an image-like data input, and then you can then run that thing in a CNN way. Or vice versa, you can convert this into a picture, so a picture can become a Fourier transform. So that this picture can become a phase by, phase by frequency map, right? And then you can say, I read it as a sequence of, because it's phase, So I can say that this frequency occurs followed by this frequency followed by this frequency, right? Because of phase, okay? Correct? So I can convert a picture into a temporal sequence as well, okay? Interchangeable. So this is really bordering on physics thing. Space and time not so different, okay? Same thing. Well, depends on how you look at it, but at least information-wise, we can imagine how we can recode spatial information as a temporal domain and temporal domain as a spatial domain, and therefore correspondingly feed it to a CNN or RNN type of computer, and then it will encode the embedding, right? The fundamental mathematical implication is that you can encode space and time interchangeably, and if there is something real, the implication there is that reality, which is in space and time in alternate formats, if it is real, then, and this is the embedding some sort of fundamental eigenspace, okay? I don't want to lose you, but if you don't get it, what it is, it doesn't matter, but some very basic space. If it is extracting whatever is in space or in time and then encoding it in some very, very basic space, which is fundamental, then it suggests that once you get it to the eigenspace, you can always regenerate space using time information or time using space information. Okay? Because it's the same thing. It's the same eigenbasis. All right? This will be advanced, and then if you do more math, then you'll get there. But the implication here, which is what this is a creative push from the previous things. You have these separate considerations, RNN, CNNs, but actually, if you think of it that way, it's actually not that different. You can use it this way. Okay? And there are implications there. All right, so those are the two, RNN, DNN, RNN, CNNs. Any questions about these two different networks? Yeah, we should be good. No? Okay, if not, I mean, if you have, you can do later, but if not, let's deal with the last thing for today and the last thing for the whole class, which is the problem of overfitting. And as we said, this is not just specific to neural networks or artificial intelligence. It is a general problem for all machine learning statistics. What is overfitting? Overfitting works like this. Agarwal has a great example. I'm just going to reproduce it here so that this is the best way to see how overfitting is a problem. So imagine I have input states like this. So I have x 1 to 5, and it is mapped to an output y. Okay? And I have x1 takes the value of 1, 2, 3, 4 over training states. Okay, over training 4 times training 1, x1 has a value of 1, x2 has a value of 1, 3, 4, 5 are 0, and y is 2. Okay, so the input is 1, 1, 0, 0, 0, and the output is 2. The next state is input is 2, 0, 1, 0, 0, and the output is 4. And so on, so forth. 6. And 8. Okay? So let's say that y, let's make y hat is equals to wi xi. Okay? So my question is, what is W? What vector or non-vector of W will give you this data table? Someone suggest? Huh? 2. Because this is a vector, right? So this is vector, vector. So it'll be 2, 0, yeah, 0, 0, 0. Correct? Yeah, so if we put x times 2, it'll always multiply every number by 2, and you will get 2, 4, 6, 8. You can see that you are a human being, very intelligent, okay? A machine could just do this actually. Will this work? Does that work? If W is 0, 2, 4, 6, 8? Right? Because just ignore the first column, right? Column 1 does not contribute. What is important are the other columns, and I just have to make my weight 2, 4, 6, 8. And then if the other column is on, I will contribute. And I don't care about column 1. Okay? So that will also give me same, 2, 4, 6, 8. Okay? So I have this one, W1 and W2. Okay? All right. Now, I'm going to give you number 5. This is I use red. I use yellow. Sorry. 5. What's the answer? What will this W2 give me? What will your answer give me? Which one is correct? Yours. So this is overfitting. The problem of overfitting. We don't know who is correct because this is non-existent in the original data. Right? It is a generalization. It requires generalization, but generalization doesn't mean accurate exactly, right? Because you didn't have data. Until it happens, you have the data, then you know whether your generalization is right or wrong. Okay? But you would think that you are more correct. Why do you think that this one is wrong? Why? What's your reason for thinking that you are more correct than the other case? Because somehow as a human, you feel like you see a pattern. Correct. And the machine feels like it's not seeing some pattern, or at least whatever pattern it's seeing is a dumber one. Right? Or at least a more restricted one. Okay, so this is the issue of, this is precisely the issue because what it is this is the local minima effect. And this is the global minimum, okay? Perhaps you, when you say that the answer is 2, you are capturing something that's a global minimum. But then the machine, in solving this local case, which might generalize incorrectly, which we do not know, might be a local minima case. It's correct. It's not wrong for its data set. Both of you are right for your data set. The question is, if you were to move beyond your data set, would you still be right? Or would the machine be right? Or the alternative be right? Which one is right? We don't know until we move. But then the question is, which one is more efficient? So for example, you can say your gut feeling is that because you seem to see some pattern. That's one thing. Another thing would be you are using fewer parameters. You see how many different numbers the other alternatives has to encode. He has to do 2, 4, 6, 8, and to use some weird idea that the first column for some reason should be ignored. Okay? Why ignore column 1? Why not ignore columns 2 to 5? Right? Why not just realize that actually 2 to 5 are not telling me anything? It seems to me that just having column 1 is sufficient. Right? More economical. So you notice that you can just use column 1. Okay? You might be wrong. Maybe the machine is right that, oh, you falsely ignore 2 to 5. You should be actually paying attention to 2 to 5. And column 1 is actually, while it's correct in the data set, it's just a distraction. It could be. We don't know until we have this data point. And even if we had the data point, we wouldn't know, right? We might see whether it's 10 or 0. Then we would know, right? Okay, so this is the overfitting problem that you can solve the local data set. But there is no way to guarantee analytically that you will be solving the global data set unless you are God. Okay. And this is the problem, as you can see, not just in machine learning, or in neural network. So in neural network is dealing with arrays and operations, right? Same thing. You can see it's also statistics, right? This is the general linear model, right? Okay, it's a true of all computational problems in that we are not God. And in statistics, the label is the population parameter. i.e. something like mu, which is the truth. It is the mean of all data points, including aliens and people you didn't sample. Whatever that number, that real number is, that is mu, okay? Which we don't know. But we have a sample statistic, i.e. x bar, which we know for our sample, and we use it to infer the population, but we don't really know the population unless we are somehow able to sample pretty much everybody. Okay? So this overfitting issue is inherent in that you come up with some parameters and you fit it, and it fits your data perfectly. But then once you try to generalize it, you may still fail. And that is the inherent difficulty. So what are some solutions to avoid it? So given this is the scenario, there is no perfect solution, only practical ones. Okay? So how do we avoid getting stuck here so that we have more than minimum chance of reaching something that might be a bit more generalizable, a bit more real? And the solutions there are many, okay? And some solutions presented are here. So very briefly, we just talk about regularization, which you already do. Okay, so regularization, which you already do, which is that you take the weights, it's equals to the alpha plus the eta. Right, these weights that you update, you don't just take them from the learning rule fresh all the time. You adopt some sort of either bias. So we have some, remember, so in the MLP, we introduce some units that are always on, and that brings the set of weights, the range of weights, to some, to some distribution, acceptable range of distribution by introducing bias, okay? Another way is to actually normalize, which you do in your VDM, right? So your weights are equals to divided by some n of, some function of the number of weights and the size of the weights as well, right? If you have a lot of weights, or if your weights are very big or very small, then your current weight is adjusted as a ratio of all those summations, okay? So you normalize that. Another way is early stopping. Instead of training your network on 1 million iterations to get all the error until it's so close to zero, you are satisfied with the model having actually some notable error. You stop it so that the weights are not perfect for your data set. So that you give it a chance to, so if it gets new data, it's not so committed to its original trained data. So you stop the training earlier. Make sense? Okay? So it's not yet gone deep into the well. It's still, it's been trained, but not so deep. And so it has an opportunity to still jump out of the well. And then the last one is deeper architecture. Agarwal, the chapter, talks about this a little bit, and I believe this is how your brain does it actually. Your brain, I think our brain does these two. Our brain has a range of energy. It cannot possibly keep firing. Up to some firing, the neuron is going to lose energy, right? Which is some sort of implementation of these two, right? The neurons can keep firing, and then at some point it can't fire anymore, and so it's been normalized or been biased so that it cannot linearly keep on increasing its activity or decreasing its activity. It has some biological energetic constraint. Basically, that's what normalization and regularization does, okay? And early stopping, okay, all these. Deeper architecture is, which Agarwal argues, is that it's better to, I don't know if you remember, but you did this exercise where you either have, your multi-layer perceptron, you have 3 units encoding to, leading to one output, or do you want to have, so many leading to one output, or versus right, you have a deeper layer, right, leading to one output. So the argument in Agarwal is that, let's say I have, the difference between 4 units versus 100 units single layer, okay, versus 4 units, 2 units, 1 unit. So I have a deeper layer. Agarwal presents that this second one, the deeper one, is actually more accurate, more efficient, right? Because it doesn't have to encode. Although this first one might sometimes outperform the second one, again, it's an overfitting case, right? It might outperform it, but it has cost it has to encode 100 parameters in order to do that. And it might overfit. Whereas a deeper layer might not perform as well locally, but ratio-wise, efficiency-wise, it can do already pretty well with much fewer parameters, and it might be able to generalize better because of that. Okay, so deeper architecture is another solution towards addressing overfitting. And you can tell in humans, it's true psychologically. If I explain this data, very complicated, a lot of conflicts, and then I cook up all sorts of arbitrary reasons. This one is wrong because in this case, the person did this and not that. this one seems to contradict that one, but that's because this person is different from the other person. So every case I come up with one individual story. I have 100 people. I have 100 different stories to account for the 100 times 100 possibilities of covariances. I will be exhausted. And likely doesn't help me to explain case number 101. However, as a human being, if I say, oh, I realize this bunch of people roughly have schizophrenia, this bunch of people roughly have depression, blah, blah, blah. Although, everyone is different. His or her schizophrenia is, this way, and his or her depression is this way, right? I don't explain everything, but I have a deeper explanation. Then case number 101, I might be able to say, this looks like a depression case, this looks like a schizophrenia case, or this looks like nothing I've ever seen before, right? And so you can imagine that might lead to a more productive solution than the earlier one. So this is, again, very, very much common sense, but just implemented in a more computational and concrete way. Okay, so that's overfitting, and that's the problem, and those are some solutions, at least, that has been suggested for neural networks, plus a recent solution extending from this deeper architecture, which I will highlight now. I might have mentioned it before, I'm not sure, but here we go. They found out, so overfitting. Of course, I can say I will create my network in LLMs, okay? Okay, so they started with this idea that, okay, I just make my LLMs deeper and deeper, right? If deeper is the solution. But this is the irony. I can, of course, go deeper and deeper and still deeper. What is the right balance of deeper? Because the idea is that should I draw accuracy, I guess, and parameters, number of parameters, okay? As we go higher and higher, accuracy goes up, number of parameters. Then this is the overfitting part. It goes down, okay? Correct? Like your GLM, at first you can predict height with weight. Then you can predict height with weight and age, and predict height with weight and age and sex and plus. And then eventually height with weight and age and sex and education and economic status and which country and all that, more and more parameters, actually your accuracy probably asymptotes or might even go down, and that is overfitting, okay? It's overfitting. So the trajectory should be this. They found, so like as you increase all that, you would expect that the accuracy ironically goes down. So our LLMs should be not too big, right? Because being too big has a problem. But the fact is our LLMs are huge, billions of parameters, yet the accuracy is pretty good. So it's like, since conflict, shouldn't it be a serious super overfitted kind of model with billions and billions of parameters? For arguably our data set might be a lot less. They found actually that it went this way. Very interesting. And the question is why? And I think, yeah, so the solution they found is basically, or the explanation they found is that when it is scaled up enough, so scaling is another solution to overfitting. When it's scaled up enough, it turned out that, remember, right? You have a delta, and the delta kind of readjusts its internal weights. One of the ways that the delta was used to adjust these weights was that it only adjusts weights that contributed to the error, right? so that if it was unit 1 that led to the error, more led to the most of the error, then when it backprop, only or more of the backprop is influencing unit 1's connections, whereas unit 2 and unit 3 are relatively stable. Okay, so at scale, what that works out to be is that maybe for this problem, this unit realizes that it should listen to only this part, and this part. And then here, when there's some problem, it realizes that it needs to listen to this part, and maybe some this part overlap as well. In other words, at scale, the later units, later layers was able to select subsections, sublayers, portions of it to generate its output, rather than have the whole model, every part of a whole model contributing to every answer. At scale, the model learned that for such problems, use this part of my model, or have more weighting from this part of my model. For this other part of problem, use other parts of my model. So it has, in a way, at scale, sort of self-regularized. It learned that certain parts of my model are more important for certain problems than other parts of my model. Again, very human. That's what our brains does, selectivity, right? In the VDM, right? We learned that when you see this pattern, tell the other people to be quiet, only pay attention to these, my local people, right? We see it at that level, and then mathematically you think that, okay, if we make this bigger and bigger, it becomes a problem. But it turns out that they discovered, that when you scale things up, essentially that operation still happens, and it happens in this format, rather than within a layer selectivity, it being cross-layer selectivity, basically. And even cross and intra-layer selectivity, right? Modular selectivity. So in other words, modularization, which is how your brain works. Your brain has modules. You don't use all of your brain in an equal weight for doing language as it does for doing spatial, computations, right? You use more left brain or right brain in terms of different types of processing. So that's very interesting. And we would not have discovered this, we would have stopped, right? If we went just by pure math, we would have stopped. But because, as we said, these are chaotic dynamical systems which you do not know how they really will behave until you implement it. So they implemented it, they scaled it, and they showed that, hey, the math the math is not wrong, the math is right, just that the math didn't account for modularization. Now we have a modularization parameter, we will be able to better predict when overfitting will be a problem or not with respect to this kind of issues. Okay? All right. Okay, last one, and then that's it. And this is also talked about in Agarwal, because we talked about this, like, okay, how does this come about? How does this modularization come about? Is because the original delta is kind of fed back to subsections differently, to adjust different weights differently. Okay, so that raises up the phenomena of what we call exploding gradients and vanishing gradients. In MLP, I'm going to do it a bit more exaggerated here. Okay, and we know that the weights, I had the formula here. Okay, and it's back propagated so that this weight is a function of weight j. Okay, correct? The upstream weights are a function of those downstream delta. The upstream deltas are a function of the downstream deltas back propagated, which means that if delta is less than 0, right? Then delta J will be greater. Oops. Correct? Because and then the weights are carried on. If delta O is greater than 0, then delta J be less than. So if this is greater than 0, or this is less than 0, if this is greater than, if this is less than 0, then as it goes on and on, it will become smaller and smaller and smaller until like basically it doesn't correct any of the original weights, the input weights. Or if it is already starting out with greater than 0, then it becomes more and more, and then it becomes more and more important disproportionately at the earlier weights than it should be. Okay, and it's hard to navigate. It's not that this is bad or wrong. It's just a result of the equation of the weights updating based on the delta, right? So we should realize this, that if not aware that this could happen mathematically as a result of the derivative propagation, you might incorrectly overweight earlier or later layers. Not that it's wrong. Sometimes it is true that maybe that if it is greater than 0, maybe it does mean that the earlier weights need to be suppressed more or augmented more. And then maybe if it's less than 0, maybe it's more the later weights that the later weights that need adjusting, and the earlier weights should be stable. Maybe some sort of balancing for either case. Regardless, we need to be aware of it. That's a result of the way that the architecture of MLP is constructed, and essentially most networks that do gradient descent, because this is the gradient descent formula. Okay. All right. So that's it. That's all. That's the whole neural networks course, and the issues, some other issues to think about. Obviously, there's a lot more. The AGOWAL chapter, we really only cover like first intro and chapter 1 and 3 or 4 or something like that, but definitely not the whole thing. If you are interested, I think it's a good resource. Obviously now internet, you can just tell AI to teach me about you, and then the AI will also be able to teach you about itself pretty well, okay? But please exercise judgment. Let me also highlight to people that we as teachers, we see a lot of people using AI, a lot of students using AI more and more, and we certainly do it in class. That is not a bad thing, but a lot of the 台大老师 and internal are trying to share with students, please use it wisely and smartly. What we mean by that is we see a lot of students, not you guys, but and since we're talking about this topic, we see a lot of students telling AI, and then they use the AI in their PowerPoint presentations, their talks, or their final figure pictures and all that. And it's a little bit obvious, very, very obvious actually, not little bit, very obvious. And we realize that students are thinking, well, the AI is already so powerful in doing that. Why don't I use it? Because it gets the job done maybe better than I can. But the assessment and evaluations, the idea of that is not what the AI can do, but what you can do, right? So putting the AI thing up there to explain that to other people is not really encouraged, okay? Because if you understand how this is just all mathematical operations, and people need to realize that it's not really that the AI still, if you just is at best what you are putting up there is what the world knows. I can just go and Google it myself, right? Yeah, when you use AI to do all your work, it is doesn't really accurately evaluate or assess your own knowledge. And I guess the point in this class, the other thing would be, I don't know, but you should be able to see a lot of parallels between what this model does and what our psychological abilities are, and you kind of in some ways reassess and reevaluate your own abilities, right? Like, hey, what is it? What is my real language ability or visual processing ability or memory ability and things like that. That's how it works. And am I really kind of, when I'm using all these tools and all that, am I really understanding it or not? We're trying to push you so that you can be much more rigorous and demand more of yourself. Now that we have AI, it's so easy to learn AI. Can we as humans push it even further beyond the boundary, right? Then that way the AI cannot take away your job. Because you can do something the AI cannot do, right? Yeah. Well, it gets harder and harder, obviously. Yeah. Okay, so that's it for me. Any questions about today, about these issues? No? All right, so then in that case, that's it. As I said, these contents for today's class are not critical for your assignments. Your assignments are already self-contained as it is. And so please go ahead and keep working on your third assignment. But of course, if these kind of inspire interesting things for you to embed in your assignment, as you've made assignment 3 more open-ended, feel free to deal with it or talk about it. As I said, I'm very much interested in each and every one of your novel ideas and applications. I think so far you guys have been doing great. So I think it's good to take this opportunity in a safe space to push the boundaries a little bit and challenge yourself. Not just for the assignment. Okay. All right, that's it. And have a great summer. And hopefully you guys have learned something useful in this class, more than just confused you entirely. Okay. All right. Thank you so much. And good luck in all your futures.